As our final DiGraph processing algorithm, we'll take a look at computing strong components. So the definition, two vertices V and W in a digraph are strongly connected if there's a directed path from V to W and another directed path from W to V. And the thing about strongly connected is that it's an equivalence relation. That is, each vertex is strongly connected to itself. If V is connected to W strongly and W is strongly connected to, then W is strongly connected to V. That just means there's directed paths connecting them. And it's also transitive. If V is connected to W and W to X, then V is strongly connected to X. To get from V to X, you go from V to W and W to X. And get from X to V, you go from X to W and W to V. So that means that since it's an equivalence relation, it divides the digraph up into sets called strongly connected components that have the property that there's directed paths connecting each pair of vertices in the set. So for example, 9 and 12 are strongly connected. There's a path from 12 to 9, another one from 9 to 12, and so forth. Our challenge is to compute the strong components in digraphs. And it's worth comparing this to what we did for connected components in undirected graphs. So this is just a quick review. In an undirected graph, if there's a path between two vertices, they're connected. That's an equivalence relation, divides them up into connected components. And what we did was, our design pattern is to build our graph processing algorithm as a constructor that takes a graph and does the pre-processing to create a table like this one, which assigns a unique ID to all the vertices in each given component, so that we can have a constant time client query to check whether two given vertices are in the same connected component or not. So linear time processing, pre-processing in the constructor to build the table, constant time client queries. And that's as good performance as we could expect to have for a graph processing algorithm. Remarkably, we're able to do the same thing for strong connectivity. It's a much more sophisticated algorithm, but the design pattern and the bottom line for the client is the same. There's a constructor that processes the graph in linear time and assigns a unique ID to each one of the strongly connected components in the graph. So one's in a component by itself, 0, 2, 3, 4, and 5, 6 and 8, 7, and 9, 10, and 12. There's 5 different strongly connected components in this graph. The constructor builds that array, and the client gets to, in constant time, know whether two vertices are strongly connected or not. It's quite amazing that we can solve this problem in this way. And as I mentioned, it's got an interesting history that I'll talk about in a second. So here's an example of strong component application. So the food web graph, this is a very small subset of that graph. The vertices are all the species, and an edge goes from producer to consumer. So if animal A eats animal B, there's an edge from A to B. And what a strong component corresponds to in this graph is kind of a subset of species that have a common energy flow. They mutually eat each other. And that's extremely important in ecological studies. Another example is, again, in processing software. Big software is made up of modules, and the vertices are the modules, and edges if one depends on another. And so a strong component in this graph is a subset of mutually interacting modules. And in a huge program like Internet Explorer, you want to know what the strong components are so that you can package them together and maybe improve the design. And again, software these graphs can be huge, and this kind of graph processing can be extremely important, improving the design of software. Now again, this algorithm has an interesting history. Along with scheduling and other things, it's a core problem in operations research that was widely studied, but really not understood how difficult it was. And Tarjan's paper in 1972 was a big surprise that this could be solved in linear time with depth-first search. Now, this algorithm had a couple of other data structures and is, I guess, a diligent student in this class could understand it with quite a bit of work. But it really demonstrated the importance of depth-first search in graph processing. Now, the algorithm that we're going to talk about today actually was invented in the 80s by Kosaraju and independently by Sharir. And the story goes that Kosaraju had to go lecture about Tarjan's algorithm, and he forgot his notes. And he had taught it a number of times. He was trying to figure out what Tarjan's algorithm did. He developed this other algorithm that's extremely simple to implement, and that's what we're going to look at today. And actually, in the 1990s, Gabau and Melhorn, particularly Melhorn, had to implement this algorithm for a big software package, and he found another simple linear time algorithm. So this story indicates even for fundamental problems in graph processing, there's algorithms out there still waiting to be discovered. And this algorithm is a good example of that. So I'll give the intuition in the code, and you see how the algorithm works. Fully convincing yourself or proving why it works is a bit more of a challenge. We'll leave that mostly for the book, but let's describe what it is. So the first idea is to think about the reverse graph. So if we take a graph and we reverse the sense of all the edges, we're going to get the same strong components. We need edges in both directions, so if we switch the directions, we're still going to have edges in both directions. The second concept is called the kernel DAG, and what that does is it kind of, you think about contracting each strong component into a single vertex, and then just worry about the edges that go from one strong component to another. The DiGraph that you get that way turns out to be acyclic. If it was cyclic, it would it would create a bigger strong component. It would coalesce a couple of strong components into one. If we think about that processing, that kernel DAG, that's the edges that go between strong components. And we get a DAG, and we know how to deal with the DAG. So the idea of the algorithm is to go ahead and compute the topological order, or the reverse post order in the kernel DAG, at least put out the edges of the original DiGraph in order so that all the edges in the kernel DAG point from right to left. That's like a topological sort. And then we run DFS, but instead of considering the vertices in numerical order for the DFS, we consider them in that reverse topological order. It's extremely easy to implement this algorithm. Of course, we're going to use DFS. So let's look at a demo at how the algorithm works. Okay, so this is a DiGraph, and our goal is to compute the strong components. And we're going to do it in two phases, two DFSs. One is to compute the reverse post order in the reverse of the graph, and the other is to run the DFS, but for the order in which we visit the vertices, we use that reverse post order that we computed. Here goes. So first we'll do the DFS in the reverse graph. That's the graph, that's the reverse graph. Remember, these two have the same strong components. There's our marked array. We do the DFS, and reverse post order means that when we're done with the vertex, we put it out. Check 6, unmarked, check 8, unmarked, check 6, it's marked, so we're done with 8, and so that's the reverse post order. And again, as before, I put it on a stack, but we'll just list them in reverse order in this demo. So 8's done, so 6, lots of places to go from 6, so let's check 7. That's unmarked, so we go to 7. No place to go from 7, so we're done with 7. We put it on the reverse post order list. We're also done with 6, because 4 and 9 are coming in this example, put it on the list. Next place to go from 0 is 2, so we check 2. That's unmarked, so we mark it and recurse, and we check the vertices adjacent to 2. First 4, that's unmarked, so then we recurse and go to 4. We got to go to 11 first and recurse, so now we're at 11. And from 11 we go to 9, which is unmarked. So we have a pretty long recursive stack right here. So from 9, we have to check a bunch of things. We'll check 12 first, and then visit 12. It's unmarked. From 12, we check 11, which is marked, nowhere to go. Then we check 10. That's unmarked, so we go to 10. Visit 10. It's unmarked, so we recurse, and then go to 9. And that's marked, and that's everywhere we get from 10. So we're done with 10. So we put it on the list. In return. And now we're done with 12, so we put it on the list and return. And now at 9, we have to check 7, which is marked, and 6, which is marked, and then we're done, so we put it on the list. Then we're done with 11, we put it on the list. Then we're finished with 4, so we check 6, which is marked, and we check 5, which is unmarked, so we recurse to 5. From 5, we check 3, which is unmarked, so we recurse. Then we check 4, which is marked. We check 2, which is marked. And then we're done with 3, so we put it on the list. And then from 5, we check 0. It's marked, so we're done with 5. We put it on the list. And that means that we're now done with 4. And then we're also done with 2 after checking 3. And then we go to 0 and put it on the list. So that's all the vertices that you get to from 0. We look for more vertices, and it's 1, and it's marked. So that's the last one in the reverse post order. So that's a reverse post order of the reverse graph. And all we're going to do is take that order and use that order to check vertices at the top level in the depth first search of our regular graph. We have to check all the other vertices to make sure we're done. So that's phase 1. So now we just do a DFS in the original graph using that order that we just computed. So we don't start with 0 the way we always have. Now we start with 1. We visit 1. It's unmarked. And now all the vertices that we visit during that DFS are going to be in the same strong component. That's the theorem that makes this algorithm work. In this case, there's only the 1, so vertex 1 is in its own strong component with label 0. So now we've got to start, 1's all done, so now we have to start with looking for another vertex to search from. In this case, it's 0 is second on the list, so that's where we start with 0. And now all the vertices that we can reach from 0 are going to have in this graph, are going to have strong component label 1. So we do the DFS. So first we get to 5. That's in the same strong component. We check 4, and it's unmarked, so we label it. We check 3, it's unmarked. We check 5, which is marked. We check 2, which is unmarked. Now we have shown that 0, 2, 3, 4, and 5 are all in the same strong component. And now we're going to find both vertices we get to from 2 are marked, so we're done with 2. Then we're done with 3. 4, we have to check 2, which is marked, and then we're done with 4 and 5. From 0, we can check 1, but that's already marked, so that's not relevant for this search. And then we're done with 0, and we've established that 0, 2, 3, 4, and 5 are all in the same strong component. So that's the second one. So now we continue and we check all of those, and they're all marked. So the next vertex in the reverse post-order reverse graph is 11. So we visit 11, check 4, it's already marked. Check 12, it's not, so we mark it, and these are the third strong component. They get labeled with 2. Then we get to 9. From 9, we check 11 and nowhere to go. Then we check 10, and so that's in the strong component. From 10, we check 12, which is marked. We're done with 10. We're done with 9. We're done with 12, and we're done with 11. So that's our second third strong component, 9, 10, 11, and 12. So we're done with those, and now we go through the list to find another unmarked vertex. 9's marked, 12's marked, 10's marked. We get to 6. From 6, 9's already marked, 4's already marked, 8's not marked, so we go there. From 8, we can get to 6, and that's it. 0's already marked, so we can only get to 8 from 6 at this point, and so that's a strong component. And then finally we finish up by doing 7. So the end of the computation gives us the strong component array, which is a unique ID for each of the vertices, so that 2 vertices in the same strong component have the same ID, and that supports constant time strong connectivity checks for clients. So the bottom line is that this algorithm is a very simple, even though it might be mysterious, algorithm for computing the strong component. First, run DFS on the reverse graph to compute the reverse post order. Then run DFS on the original graph, considering the vertices in the order given by the first DFS. These diagrams give a summary of the computation. I'm not going to spend too much time explaining why and how it works in this lecture, but these kinds of diagrams give the detail that can give some intuition about how and why the algorithm works. For the proof, it requires some mathematical sophistication, and you'll find it in the book. But the programming of it is quite simple, and prove that it's efficient all it does is run DFS twice. But to really see the correctness proof, you want to look at the second printing of the textbook. We got it wrong in the first printing. But look at the implementation. So this is connected components in an undirected graph with DFS that we did last time. And I'm sure many of you thought it was one of the simplest algorithms that we looked at. We just mark the vertices and do recursive DFS, and that's the end of it. If you take that code and just add, well, change the names, and then just instead of going for the vertices from 0 through v minus 1, if you first compute the depth first order that you get by running, doing a depth first search of the reverse graph, and then you iterate through the vertices in that order, you get an algorithm for strong connectivity. It's really remarkable that just changing that one line will perform this computation that was thought to be difficult for many years, and people were learning quite difficult codes for it for many, many years. So that's a quick summary of DiGraph processing. We talked about single source reachability, getting the paths from a vertex to any vertex that can be reached from that vertex with a directed path. We talked about topological sort in graphs that have no cycles, and that uses DFS. And we talked about computing strong components in a DiGraph with two DFSs. DiGraph processing is really a testimony to the ingenuity that's possible in algorithmic graph processing.